Hi, Isabel. How are you? Hey, I wanted to give you an answer and use some graphics in this problem is because they're asking you to use graphics, and I wanted to show you how to present the answer in graphical form, also in mathematical form. Okay. So here you've got a wire, or you've got a wire and has a current on it. Let's say, what was it? I equals 1.15 amperes. Now, just to refresh your memory, that amperes is nothing but coulomb per second. Okay? Because I is equal to Q over T, and the charge of Q is coulomb, and charge of T is second. So I is nothing but coulomb per second, or ampere. Okay, so I'll make that clear. So you've got this wire. Let's say this is the x-axis, and this plane here, P. And you also have a magnetic field with a value of B, which is basically directed in the magnetic field is directed in the z direction in the plane. So you got a z direction here, and you've got the x direction where your your charge or the current is running through. And so this can be represented as velocity v vector, which is basically running in the x direction. And this magnetic field is also a vector, and it's running in the z direction. And the beta is given to you, B is given to you as, what is it? 1.5 Tesla. 1.5 Tesla. Now, Tesla is nothing but the unit of the magnetic field, and Tesla can also be written as 1 Tesla is equal to 1 Newton times second per coulomb meter. Okay, so that will be your magnetic field. It's also equal, Newton per coulomb is nothing but, second per coulomb is the reverse of coulomb per second, so it is 1 Newton per ampere meter. Okay. Now, why am I doing all these units? You're going to see that when we do compute the force, you're going to have to, the units have to basically match and have to cancel out. Okay. So the force in this system is going to be in Newton. Now, we do not know what it is yet, but we're going to find out. Okay. So here is telling you that because of the magnetic field is running in the z direction, and the current is running in the x direction, therefore you use the right hand rule. Now, what's right hand rule is we'll take V and we cross it with B. We take V and cross it with B, and we will get, based on the right hand rule, the direction of the force is going to be up like that. Okay, let me draw that in different color. Let me draw that force in magenta. Okay, so This will be your direction of your force right here. And so what would be the magnitude of the direction of the force? Well, the force, so that basically answers, this graphic answers part A of your question, which is show me a schematic of what the magnetic field crossing with the current, what's the direction of the force, and this is the direction of the force. It's that force is perpendicular to the plane P, in which the vector B and the vector V are in different z and x-axis, but they lie in the same plane. Therefore, the vector F is a perpendicular vector to the plane P, and whose magnitude is, we're going to find out in a second what the magnitude of the vector is. Well, the magnitude of the force, let me change the color to blue. The force, I think in the second part of the question, he's asking for the magnitude of the force. Let me check your second part of the question before I go further here. I'm still with you, just bear with me a second. I'm looking at the original. There it is right here. So draw a table diagram of the situation. We did all of that. What's the direction of magnetic force on the wire? Tell the factors on which the direction depends. We talked about that. It's basically the using the right hand rule, curling your finger, using your right hand, curling your finger from V to B, okay? And then what's the magnitude of the magnetic force acting on 1.25 meter long section of the wire? So we basically answered A and most of B. Let me go back to our recording here. The magnitude of the direction of the force is up, perpendicular to the plane P, which carries both vectors B and V, where V is in the X direction and Z in the Z direction, but both directions are in plane. So this plane is actually plane XZ. This plane is plane XZ. So you can imagine if this is XZ and Y, there's a Y direction up. This will be in the positive Y direction. The force, which is going to be perpendicular to the plane, which contains the two coplanar vectors V and B. Okay? So what is the magnitude of the force? And that's your last part of the question. Well, the magnitude is V vector times Q, which is the charge value, UV, cross product B, sine phi. Okay, so let's just see. We do not have Q, we have I, okay, and we do not have V either. But you got to remember that, like I said, I is nothing but, well, QV. Let's put that here, QV. Well, the charge Q is in Coulomb, okay? And the velocity V is in meter per second. So this value here should be in Coulomb meter per second. But we know that Coulomb per second is amp, okay? So it will be amp times meter. So the unit of the QV is also amp times meter. Now, what does meter mean? It means a distance. Now, we can call that distance x. We do not know what it is. Or yes, we're given the distance. So A times that x distance. And that, if you want to call that ampere, which is ampere, will be I times the distance d, or x. Let's call it d, because I don't want to confuse those units. I'm going to call that distance d. Okay, so it will be id, and will I as a vector cross b times b. Let's not call that cross, call it times b. Well, actually, it's a cross product, because in order for you to get the vertical direction, you have to use the cross product and the right-hand rule. Okay, times sine phi. Now, phi here is 37 degrees. So notice, as we curl our finger from V to B using the right-hand rule, we get our thumb up. Now, that thumb up is that direction of the force F, which is perpendicular to the plane that you're seeing here. So now we have everything we need to put the numbers on this. I, it's given as 1.15 ampere. The distance D is given as 1.25 meter. Okay. And B is the magnetic field, and it's in Tesla. And we said that Tesla was 1 Tesla is equal 1 Newton second per Coulomb meter, or 1 Newton per ampere meter. So we will put that value as 1.5 Newton per ampere times meter, and sine 37 degrees. So we do all of this calculation. Let's see what we have here. Ampere, I'm going to use a different color. I'm going to use red and use this. You can see here that ampere and ampere cancel out from the equation. Meter and meter cancel out, and you're left with Newton. So you multiply all of this, and you get 1.15 times 1.25 times 1.5 times sine 37. I got 1.297. I'm going to call it 1.3. I'll call it 1.3 meters, 1.3 newtons. 1.3 Newton, direction up and perpendicular to the XZ plane. Okay, I believe that is your answer for this question. If you like what you see and how I explained this for you, you can contact me for other lessons if you like. Okay, take care. Bye.